So we'll just continue talking about our modified starches. So already we've talked about converted starches. And the first one we talked about was this acid modified starch, which anyone remember what those properties are of a acid modified starch? This was an example down here, the gumdrops or the candies, that's where it's used. So, you know, overall in this section, I really would like you to sort of remember the major functions and uses of each of these starches. I think it's really important. And I do feel like a lot of times we go through these and then I ask, you know, what is this starch's functionality, or what types of products is it used in? And I get like kind of crickets. So, yeah, you know, just like when we were talking about preservatives, I said, you know, you really want to know which microbes each of these preservatives is inhibiting. Is it inhibiting bacteria, yeast, or mold? Here, what you want to know are the functional properties and the uses. So here, acid modified starches, they're thin boiling, and then they create an extremely strong gel once they've cooled. So those are the unique functional properties of acid modified starches, which makes them good for these types of candies because you can pump them through pipes into molds, and then once they get into those molds, it will form a very strong gel. So we ended last time talking about degree of dextrose equivalency. And I went through it, but I think maybe it was a little fast. So the equation for dextrose equivalency is very simple. Just the degree of, or it's 100 divided by the degree of polymerization. So if we take glucose, for instance, it would be 100 divided by 1, because it's just a dp of 1. And so that would be 100, which, if you don't know, dextrose and glucose are synonyms. So those are the same compound. Dextrose is just an old-fashioned name for glucose. So this could be called glucose equivalency, which should be 100. And then the rest of these, maltose, you know, maltose is 2 glucose units linked together. So the degree of polymerization is 2. And so dextrose equivalency is 100 divided by 2. So that would be 50. And corn syrups, generally corn syrups have a lot of glucose in them, but they do have a little bit of longer polymers, maltose, maltotriose, maltotetrose, and so on. And so their average degree of polymerization, this average here, would be something between 20 and 35. So yeah, and then maltodextrins, those would be those, you know, short polymers of glucose. So a dextrin is a short polymer of glucose, or of starch, and a maltodextrin would be the general term for that. And dextrose equivalency of less than 20 would be a maltodextrin. So basically, an average degree of polymerization of 5 or more would be a maltodextrin. And the maltodextrins, you know, I mentioned some of the functional properties. They're in foods for to generate body in beverages, for instance. they're binding agents, they're fillers, filling agents. As I mentioned, the artificial sweeteners like sucralose and aspartame. When you buy those in the store, most of that product is maltodextrin, which will make it seem like you're putting something on your food instead of nothing, which would be the case if you had the straight compounds. Okay, so let's go to esterified starch, which is commonly called stabilized starch. And I think that's on a previous slide, but I can write it here. So we take starch and we react it with this compound, which is acetic anhydride. This is the anhydride linkage here between two acetate groups. And this, any anhydride bond is very unstable. It will break down immediately in water. But if we have, hydroxyl groups around, it can react with those and form an ester, this ester link here. And then you have another acetate left over. So when we do that, we will introduce these, shown here in this picture, these blocking groups, which because of this methyl group here have some hydrophobic characteristic to them, and they're also bulky. And so we prevent retrogradation, which means that we prevent syneresis. So these starches are really good in things that are gonna go through some abuse, especially like frozen foods. So frozen foods that may exhibit some freeze-thaw abuse, we can use esterified starches to prevent the gel from losing water or prevent syneresis. So let me write a few of those things. So first of all, if we want to make this starch, we would first make a starch slurry. That's probably 30 to 40% solids. So got a lot of starch in there, just a little bit of water. And then we're also going to put in like 30 to 40% of some salt. So it could be sodium chloride, could be sodium sulfate. So, and these two compounds, they don't do anything. They're only there to tie up water. Because remember I said this thing breaks down in water. So we need to remove as much water as possible. So we go high solids content, and we go with a lot of dissolved solids to trap more of that water. And then we're going to have a pH of something above 8.5 maybe, something like 9 or above. So a slightly alkaline pH. That's going to help drive this reaction better. And then we're going to heat that up to maybe 50 to 60 degrees and add our anhydride. And it's acetic anhydride in this case. And that's going to react for a period of time, depending on how many of these groups you want to add onto the starch. And then so then you're going to neutralize, wash it, and dry it. So that's how this starch is produced. And its functionality is it's called a stabilized starch. So it must be stable. So it's stable to freeze, thaw, abuse? It's going to have a very high peak viscosity. So that's the opposite of the converted starch that has a thin boiling or a low peak viscosity. This one has a high peak viscosity. And so it's useful in frozen foods, condiments, things where we don't want syneresis to happen. I haven't mentioned yet. So cereal starches are generally cloudy when you cook them out. So they have a gel that's kind of opaque or white in appearance. And anytime we do any of these chemical modifications, whether it's acid modified, esterified, some of the other ones we're going to talk about, phosphorylated, etherified, any of these modifications, they are all going to improve the clarity of the gel. And in general, we want clear gels instead of cloudy gels. So this functional property right here, improved clarity of the gel, is not really unique to this starch. Any modified starch would have an improved clarity. But the use here is specifically in gelled foods that might have some abuse. So I mentioned that you can do the reaction for as long as it takes to get, the number of acetate groups that you want on the starch. So a question could be, how many acetate groups do we put onto the starch? And so the degree of substitution is a term that describes how many of those acetate groups or any substituent that you're adding to starch, how many are attached to the starch. So it's just the moles of the substituent. So for this starch, it would be the moles of acetate groups that you have per mole of anhydroglucose. And so here I have a picture of starch. And this in brackets here would be an anhydroglucose unit. And it's anhydroglucose because we took out water to create this glycosidic linkage. So it would be called anhydroglucose. But in this molecule, which represents all but the reducing end and the terminal glucose unit, has 3 hydroxyl groups shown here with these asterisks next to them. So those 3 hydroxyl groups are what can react with the acetic anhydride. So according to this equation, what is the maximum degree of substitution that we can have for a modified starch? Anyone want to guess or tell me? I do have the chat open, so I can see if you type something into the chat. Okay, yes, I can repeat the question. So I just mentioned what the equation is, and I mentioned that we have these 3 hydroxyl groups that can be substituted. So the question is, what is the maximum degree of substitution that you can have in starch? Good. The answer is 3. Several of you answered that correctly. So you have 3 hydroxyl groups on each anhydroglucose unit. So the most you can get is 3 divided by 1, which would be just 3. So that's the maximum. So then, and another question, which I don't expect you to know or answer, is what is a typical degree of substitution? So for acetylated starch, or this stabilized starch, the maximum degree of substitution that's allowed, according to the Code of Federal Regulations, is 0.09. So if you kind of say that in an easy way, 9% of the glucose units can have an acetate group on them. So if we just round that to 0.1, so we can do easy math, if we have a degree of substitution of 0.1, that means that 1 glucose unit for every 10 has that modified substituent on it. So, but the maximum for acetylated starch would be 0.09. And most acetylated starches that you'll buy don't actually go to the maximum. They're somewhat less than that. So for acetylated starch, we have something less than about 1 in every 11 glucose units having an acetylated, an acetyl group on them. So most of the glucose units are still just normal. And so that's kind of shown here. We just have one of these for every 11 or more glucose units. So not extensively substituted, but nevertheless changes the functional properties a lot. And we'll see that for all of the other modifications, the degree of substitution is even less than 0.09. So for this one, this is octanyl succinylated starch. So we react starch here with octanyl succinic anhydride. So this is an anhydride that is formed within one molecule. So it's a intramolecular anhydride. And when we react that octanyl succinic anhydride under the same conditions that I talked about for the stabilized starch, then we get this type of compound here. And this substituent adds some pretty unique functionality to this starch. First of all, over here, this is a hydrophobic chain, right? So we've introduced some hydrophobic characteristic to this starch. So this will help in high-fat foods. It can help for emulsification because of this. This group here is charged. So now our starch is susceptible to pH changes, to ionic strength. So this ionic group here can interact with metals that are in the food, and also it changes the solubility of this starch based on the pH. So higher pH would be more soluble. As the pH is lower and this becomes protonated, this starch would become less soluble. All right, next we have phosphorylated starch. And there's two types of phosphorylated starches. So we do want to make sure that we keep track, or that we know the difference between the two. So this starch is a monoester. So we just have one ester group and one starch molecule. So it looks like this. So to make this, we are going to, I don't have anything to type here. I should have put a box. So the reactants here, maybe I can type it in the chat. Check the chat, I'll type it in. So we have two reactants. We can have sodium tripolyphosphate, or we can have sodium orthophosphate. So these phosphates are not particularly reactive. We are going to mix them in very high concentrations with very high concentrations of starch under slightly alkaline conditions, and we can get them to add to the starch, form the starch phosphate. And phosphorylated starch is actually naturally occurring starch. So they occur in potato starches. So potato starches have a very small amount of phosphorylation on them naturally. And so, but the cereal starches don't. And, you know, most of these modified starches are corn starches, which doesn't have any phosphates. So we can add those to the corn starches and get that functionality. So phosphates are going to introduce, again, some polarity. You know, these can be ionized, so it's going to be susceptible to pH changes and ionic strength. I guess since I don't have a box, I'll type into the chat again. These starches are going to have very high viscosity. I can type it, high viscosity. Just like all of them, we're going to have clarity of the gel. We're going to have improved stability. Okay, so a lot of these properties are similar to acetylated starch. So this is why this starch is also called a stabilized starch. So they would have similar functional uses to what I mentioned for acetylated starches. So frozen foods that we need to really prevent that syneresis from happening. But unlike the acetylated starch, these starches are going to be susceptible to pH changes as well as ionic strength because of the polar nature of the substituent group. Okay, so these are the distarch phosphates. So notice where the di is, it's on the starch, it's not on the phosphate part. So we have two starches, and sometimes we have two phosphates, but not necessarily. Okay, so to react or to make these, we would take starch and react it with either this metaphosphate here, trisodium metaphosphate, or this compound, which is a chlorinated phosphate. This one is called phosphorus oxychloride or phosphoryl chloride, same thing. And you know, these halogens here, these chlorine groups make this phosphate extremely reactive. And then this, you know, this is a phosphate anhydride right here. So we have actually an anhydride bond here. So this is also very reactive with hydroxyl groups. So both of these can react. And because we have all these phosphate anhydride groups here, there's 3 of them here, then we can actually react in several places with starch. So that's shown here. We've reacted in several places with this starch. And so now we have 2 starch molecules hooked together. That's why we have the distarch. We can also react on the same phosphate and get just one phosphate cross-linking the two starches. And then the other phosphates would just be lost. Or we can get, two chlorine atoms here on this phosphate to cross-link the starch. So we can get, I guess, distarch diphosphate or distarch monophosphate. But the point is here with these two reactants, with the metaphosphate or with this phosphoryl chloride, which is also called phosphorus oxychloride, if we use this as a reactant, then we get a cross-linked starch, or this distarch phosphate. So these are going to have very high viscosity, as you can imagine, because we take two polymers of starch and actually link them together. So we're kind of solidifying that web of starch to create a very high viscosity and high strong gel. We delay gelatinization. So this is the key functional property of these starches here. Delay gelatinization. So that's what makes them helpful for use in canned foods or foods that will be heated extensively. So when I say delay gelatinization, so typically starches, they're going to start to gelatinize somewhere around 60 degrees Celsius. So if we have a degree of substitution of 0.002, so that means that 2%, or 0.2%, I'm sorry, 0.2% of the glucose units in the starch have a phosphate group attached to them. So not very many. But that low degree of substitution will prevent gelatinization up to 100 degrees. So this is why they're useful in these canned foods, because those canned foods are going to be exposed to temperatures above 100 degrees. And so these starches will be able to cook out, but they don't cook out early in the retorting process. They cook out late in the retorting process. So this is advantageous because the product inside of that can is going to retain a low viscosity for a longer period of time. And so the heat transfer is going to be better. And so the processing time is going to be shorter. And so the quality of the product is going to be better. So if we can make this starch, we do want it to cook out because we want the product to be thick at the end. But if we prevent that gelatinization until later in the retort process, then that viscosity will be low for longer, and that heat transfer into that can will be better so that we don't have to process that can for so long. Okay, here's a mixed anhydride here. This is an anhydride of acetic acid on either end, and then in the middle you have adipic acid. So this is acetylated adipate, or acetyl adipate. So a mixed anhydride. So if we mix that with starch, this is another way that we can get cross-linked starch. So here's that cross-linked starch with the adipic acid in the middle there, connecting the two starch molecules. You know, you get lots of products with this. Sometimes you get acetylated, sometimes you get just adipated starch, but you can get the distarch. So this type of product would have a functionality that would be a hybrid between a cross-linked starch and an acetylated starch. So it would have resistance to syneresis. It would also have very high viscosity and delayed gelatinization. Next, we have oxidized starch. So it's very common when producing starches to treat them with some oxidizing agent to remove the color so that the starches are pure white. You know, corn starches will generally tend to have like a little bit of yellow in them. And so to get rid of that, starches are often treated with a really dilute oxidizing agent, typically hydrogen peroxide. And that will just remove the color, but it doesn't actually change the starch at all. So if you did that to, you know, treat a starch with really dilute hydrogen peroxide, that's really just to remove the color. It doesn't change the functionality of the starch at all. But if we treat starch with a stronger oxidizing agent at a higher concentration, then the starch itself can become oxidized. So in this example, we're using sodium hypochlorite, which is just bleach. And if we use the sodium hypochlorite with starch, we can oxidize the glucose molecules and produce a compound like this. So the actual structure or the actual changes that occur are, you know, varied, but in general at carbons 2 and 3 we get some oxidation and also ring opening. So this is not a ring anymore. And we can get aldehydes forming, as I show here. We can also get carboxylic acids forming if we further oxidize these aldehydes. So this type of modification will produce a starch that has the same functionality as an acetylated starch. So the uses for oxidized starches would be the same uses that I mentioned for acetylated starches, which are products that need a thin boiling mixture or a product that needs a very strong gel. Oxidized starches are more efficient than acetylated starches. So whatever an acetylated starch, I'm sorry, I made a mistake. These have the same functionality as converted starches, not acetylated. I think I mentioned the functional properties of converted starches. So thin boiling, strong gel at the end, clear gel. So these are the same as converted starches. Please correct your notes. But they're more efficient than converted starches, so you have to use less. So they're more expensive, but they are more efficient at doing their job. So oftentimes the increased cost is offset by the lower amount that you need to use. And also they're, you know, one might argue they're a little bit better at doing what they're supposed to do than the converted starches. You know, they have an even clearer gel, and the final gel strength is even stronger than a converted starch. But they do generally cost a little bit more. Okay, now we have two non-chemical modifications that we'll talk about. So the first one is pre-gelatinized starches. So pre-gelatinized starches are simply starches that have been pre-gelatinized and then dried, or they've been cooked and then dried. So in this picture on the left here, this is the typical way to produce a pre-gelatinized starch. So you would have a starch slurry up here at the top, and it would go through this pipe. And this starch slurry would just be starch and water. And it's raw starch at this point. So not soluble or anything, just feeding through this pipe. And then it comes out here, and then these two black circles here are big drums that are filled with steam. So they're super hot. And they're rotating like this, in this direction towards each other. So rotating here, this one rotating this way. So as this starch comes through here, it will be deposited, or it will come in contact with these heated drums. And as soon as it comes in contact with that drum, it will simultaneously cook and dry. So, you know, right here at the very beginning, you've got a lot of water and some starch. And so that water there cooks the starch. And then because this barrel here that's rotating is heated, that water is going to evaporate and dry out the starch. So you have this film of starch that is on the surface of this drum. And then it comes to this point where it's finally dry, and there's going to be a knife here that will just scrape the dried starch off of that drum and then be collected over here. It'll just scrape it off over here and be collected. And then, you know, it'll be kind of flakes, and then it's just milled into a fine powder again. So these pre-gelatinized starches are going to have the same functional properties as whatever starch you started with. So you could put a native starch up here, or you could put a modified starch up here, and you could pre-gelatinize it. And it would retain the same functional properties that it had before. The advantage of these is that now all we have to do is put them into water, and they will be thick, or it will create a gel. You don't have to cook it anymore. You do have to be careful about how to dissolve it, and we'll talk about that in just a minute, or maybe next week when we start talking about gums, because sometimes dissolving them can be difficult, but you don't have to cook them out because they're already cooked. And they do have the same functionality that that the original starch had. They do lose a little bit, you know, say a little bit of viscosity, but in general, same functionality. On the right here, this picture is just showing another way to make these pre-gelatinized starches. This is an extruder. So you have starch coming in. It's going to be maybe 30% moisture, something like that. And then it will just go through this barrel, the extruder barrel, which is heated, and then come out here, and it will be cooked out. You'll then dry it down and then mill it into a powder. So both of those are typical ways to make pre-gelatinized starches. Useful in, you know, instant soups, instant puddings, these types of products that are intended to be mixed with, cold water or milk or something, and then form a gel. Next, we have another physical modification, which is a cold water swelling starch. And don't get these two mixed up. This one, this starch, pre-gelatinized starch, does swell in cold water, but it is not a cold water swelling starch. So cold water swelling starches are made by taking starch, granular starch, and mixing it into a non-solvent, commonly ethanol. So you would mix starch with ethanol, and then you would heat it to a really high temperature, like 120 degrees Celsius. And you would do that for a really long period of time, like several hours. And then once you have cooled that and removed the ethanol, that starch has some strange functionality, which is that when we put those starch granules, so these are still granular, they haven't been cooked because we heated it without the presence of water. When we put those starches into water, they swell in cold water. So if you remember the RVA curve, where we heat it to about 60 degrees and we get to that max viscosity. So cold water swelling starches reach that max viscosity in cold water. And so they just take on water in cold water and fill up the space that you give them. But they are still granular. They have not been cooked out yet. And so these starches would still need to be cooked in order to form, a viscosity that will last or a gel. So these starches are really useful in many products in the industry where you have particulates that may sink to the bottom of a cooking kettle or a depositor or something like that before it goes through the heat process. So for instance, like a tomato sauce or a pasta sauce, or maybe a pancake or waffle batter that has blueberries in it or something like that, chocolate chips in it. So these types of products, either that marinara sauce or that pancake batter, you would have all these particulates in there that potentially could sink to the bottom of the vessel that you're holding them in before they go into wherever they're going to be cooked. And so if you add a cold water swelling starch, that will create some viscosity in that raw product so that those big particles, either the blueberries or the chunks of tomatoes or vegetables or chocolate chips, won't sink to the bottom before that product has a chance to cook. So that's where these starches would be useful. But the key thing here is that you have to remember that these are still granular starches and they still have to be cooked out before they are going to have their actual functional properties. Okay, that brings us to the end of starch, and I'm looking at the clock. I have only 3 minutes, so maybe we'll just go through this first slide and then we'll end, and then next week we'll talk about polysaccharide gums. So polysaccharide gums, in my opinion, could be classified both as carbohydrates and as food additives. So I think it covers both of the topics that we're covering in this exam. And so maybe we've transitioned into food additives again. But here we have, these are the two main functional properties that we want with polysaccharide gums. We want thickening and we want gelation. So those are the same functional properties that we want with starches as well. So these polysaccharide gums are going to have similar functionality to starches. They generally are a lot more efficient though. So whereas starches, you may need 5 or 10% starch in order to get a really thick product or a gel, with polysaccharide gums, you generally need 1% or less. These functional properties down here at the bottom of this slide are secondary functional properties. All of these things are other functionality that you might get from a polysaccharide gum that would probably be important, but they would generally be secondary to either thickening or gelation. So this is why I want to go over this now, and then we'll go into polysaccharide gums later. And this is because we just talked about pre-gelatinized starches. So pre-gel starches, again, they have the same functionality as their original starch, but they do that in cold water. And so you have to be really careful when dissolving either a pre-gelatinized starch or a polysaccharide gum in water, because you can get something called fish eyes that we'll see in the next slide. So this slide is just showing here what happens when you dissolve sugar in water. So sugar are crystals, and those crystals just get smaller until they're all the way dissolved. But gums don't come in crystals, they come in particles. And when we put those particles into water, they swell. And if we have those particles too close together, then they all stick together. And we form what's called fish eyes, which are very undesirable. They're basically chunks of dry gum that are floating in your product that, first of all, aren't creating viscosity, and they also have this really disgusting lump there. So we need to I'm missing a slide here. We need to dissolve them in an appropriate way. And so one way to dissolve them is to physically separate them from each other. So in a dry soup mix or a pudding mix that has either pre-gelatinized starch or a gum, we can put a whole bunch of other ingredients together with it. Sugar, salt, dried vegetables, spices, whatever other things there are. And if we mix those other things together with the gum or the pre-gelatinized starch, it will separate all those particles so that when they go into the water, they're far enough apart so that they don't stick together like this. So that's one way that we can dissolve these gums more easily. Okay, we'll end there. I'm going to go ahead and add those 2 slides that somehow got lost, and we'll talk about other ways to dissolve these gums or pre-gelatinized starches next time. So, okay, we'll have our review on Friday or Thursday or Friday, depending on your time zone. And I think we'll probably cut the study guide short. So the last few questions I don't think we've covered yet. So when we talk on Thursday or Friday, we'll just cut off those questions from the study guide and probably just add them onto the study guide for next week. So, but I'll let you know exactly which question we need to get to in our review next time. All right, thanks everyone. Sorry, for those of you that we usually meet in person, sorry I couldn't do that today. I will see everyone on Zoom on Thursday or Friday.
Thank you, Dr. Rose.